Hey everyone, today I would like to talk to you about the different transformer architectures that we find in the literature and in use these days. So transformer at a very high level consists of both an encoder and decoder. And through the progression of the research on transformers, people have decided to use only encoders, only decoders, encoder decoders, or uh, combinations of these, right? So today we'll look at the different types of combinations that you can look at. So let's look at the only encoder architecture. So we have an encoder, you have an input, typically a sentence, and you get an input encoding, a sentence encoding, or paragraph encoding as your output of this encoder. And this can be used for parsing the input for any downstream tasks, right? For instance, if you want to do sentiment analysis, you encode a paragraph or a review, and then you use an input encoding in a downstream model, and then you can derive the sentiment. Or you can also summarize a document the same way. You can ask extractive question answering the same way. So some of the popular models that are used for encoder only transformer architecture include BERT, which is a classical starting point for encoder architectures. And then you have variations of these, such as Roberta, more highly optimized BERT, distal BERT, a more compressed, easier to handle memory-wise model. And you also have SBERT, which is very good for encoding sentences and getting concise representations for sentences. So as we said, some of the applications are document summarization, sentiment analysis, token classification. You have different tokens and you want to classify them. So the main thing here is that with transformer is if your input has 100 tokens, you're going to get 100 token embeddings as your output. So it's going to preserve the dimensionality of the input sequence size, right? And so you can take each of the token embeddings on the output and do parts of speech tagging, like what's a noun, what's a verb, what's a place, what's a thing in the sentence, and also named entity recognition, what entities exist in this sentence, such as restaurants or places, etc. Extractive question answering, so you have a document and you have a question, and that's passed as an input. You can get an embedding from that question answering input and then use that embedding for downstream task of answering questions. But this is extractive in nature, so the answer is going to be from the text that's already present in the question. And then you can also do image encoding. This is, for instance, through the use of V-transformer, which is visual transformer, which takes in images as input and produces image encoding, which can then be used for downstream tasks, such as image captioning or image classification, for instance. So that's the encoder only architecture. The second one is the encoder decoder architecture. So this is the full transformer, you can say, which uses both the encoder and decoder. So here we have the input, you start with the input and then you get the encoded input through the encoder. And this is also passed in as cross attention to the decoder. And there's a decoder input, which could be empty to begin with. For instance, if you're translating a sentence from French to English, the French encoder is going to give you a French encoding of the sentence. And then from that encoding, your decoder input is going to start empty, but then it's going to start generating words in English so that you can translate the French sentence to English. And one of the key things about transformers is that they use attention. So there is self-attention in both encoder and decoder, but in the case of encoder decoder architecture, you also have cross attention between the encoder and decoder. So some examples of encoder decoder architecture that's used is translation, abstractive generative question answering. So abstractive and generative are the same things. Abstractive or generative summarization. So if you want to summarize a document, but you want to summarize it in your own words, that's abstractive. Or you want to answer a question, but in your own words, that's generative. For instance, if you look at ChatGPT, that's generative question answering. So some of the popular models here are BART and TFI. So that's encoder decoder architecture. Let's move on to decoder only architecture. So in decoder only architecture, and this has become really popular with GPT. So wherever you see GPT, GPT 3.5, GPT-4 that got released recently as well, are heavily dependent on the decoder-only architecture, where you don't have to use an encoder because you care more about the generation aspect. You want to generate responses to questions. So the focus is more on generation than discrimination. So in research, people have found out that decoder-only architectures do really well on question answering tasks. So here you pass in an input and you have self-attention on the input, but only on the input you've seen so far. So this is autoregressive self-attention. And the decoder, in an autoregressive way, which is looking at the past, it's generating the next word. Looking at the past, it keeps generating the next word. So in an autoregressive manner, it's going to generate the output one token at a time. And that's what we see as an output when we type in something into ChatGPT. It gives us a response. That's the autoregressive format of generating word by word a sequence of words, which then become a paragraph or a document or a sentence. So that's the decoder-only architecture. The main application of this architecture is question answering. So for instance, we see with it, this is the case with ChatGPT or GPT-4 or GPT 3.5. Obviously, the main task that this architecture is trained on is language modeling. So next word prediction, next sentence prediction, and so on and so forth. So understanding language really well and being able to generate and fill in missing pieces or the next sentence is something that the decoder-only architecture is really good at doing. Okay, and then we have the Encoder Encoder architecture. So this is something new, but I wanted to tie it up, in one place, because this is not something that we see as a typical application of transformer, but this is something that gets used specifically in recommender systems. So if you want to find products that are similar, given a product, find other products that are similar to this product. Like given a paper towel, find me other products that are similar. Maybe you have some cleaning products that are similar. So there, an encoder architecture is useful. Retrieve products for a given query. So you have a query and you want to retrieve products for a given query. Then you can use an encoder architecture as well. Similarity search and more broadly recommender systems. So in the encoder architecture, you have two encoders. So you have encoders in parallel, and these could be exactly the same, in which case you call it Siamese architecture, Siamese twins. So both of these encoders are going to encode the inputs, respective inputs, and you're going to get encoding 1 and encoding 2. And then you do a cosine similarity or some filtering on top that can help you understand if input 2 is close to input 1 or not. So that's the encoder architecture. So in summary, we looked at the transformer architecture in 4 different ways. One is the encoder-only architecture, encoder-decoder architecture, decoder-only architecture, and encoder-encoder architecture. And these have different applications, different sets of models. With the encoder-encoder architecture, you will hear the two-tower architecture as a very popular rephrasing of this, especially in the context of recommender systems. But when you also have language, two-tower architecture is equivalent to an encoder-encoder architecture. So we looked at these 4 different architectures that fall under transformers. So hope you enjoyed the video today. Catch you later.